So I'm going to make a small video here on IUT definition 6.1.I, and so this is on FL groups up to some identification, and FL Torsors up to another type of identification. So let me explain what these objects are. Okay, so let's make a definition. So I'm going to define a category. The category of groups isomorphic to FL modulo this equivalence is defined by the following. So to define a category, we define the objects and morphisms. The objects of this category are polymorphisms. So a polymorphism is a collection of morphisms from a set to another set. So this is, I'm going to use two arrows to denote polymorphism. So this is polymorphisms from a set E to the module, let's say the Z module or abelian group FL. Okay, and so these are the objects, and the morphisms of this category are, so what we can write it as such. So we have two of these guys are equivalence classes of maps of sets we'll call them alpha. And so if we have one of these things, we really have this F and this pairs of F's, and then E and F. So this goes from the domain of the first one to the domain of the second one, such that the following condition holds, that this set of polymorphisms is equal to this set of polymorphisms composed with alpha. So just this composition condition. So another thing to think about is that here F, what's this notation? F plus minus. So this is really plus or minus 1 times some fixed 1. Okay, so this is the set of F in minus F. Okay, so we have two. It's a set of maps, and we have two of them here. Okay, and so this is this category of groups isomorphic to FL modulo this identification. We should check that composition of morphisms makes sense. Composition. Okay, so let's take a bunch of them. So we take alpha, G, and then we'll have some beta. And okay, and then this is a morphism and this is a morphism, so we write down this condition. And we write down this condition. H plus or minus composed with beta. Okay, and so we can plug in this one into this one. And we get H plus or minus composed with beta composed with alpha. And so this makes sense. So this map here is what it's supposed to be. So this is beta or alpha composed with beta. Okay, so you first apply alpha, then you apply beta. Okay, so this is okay. All right, I think the sound might be weird, so I'm gonna switch real quick. The sound seems okay, so I'm just gonna continue. So I checked the composition. Okay, and now I've kind of already been using the notation, but let's introduce some notation. So if F here, this guy here, is a FL group modulo plus or minus 1, then we may just may denote it by E or just simply F. Okay? In this case, okay, so in this particular situation, we'll let E be E of F and F be F of E. Okay, so like if I just specify E, then I can write F of E like so, or if I just specify F, I'll write E of F like so. And we already saw this before up here. Okay. So the next thing I want to say is that there's a functor and we'll call it M. So if we take the category of FL groups up to plus or minus 1, and there's a functor here to modules over FL, and the idea is that there's this functor exists because this thing here, E to FL. So I guess this has a well-defined module structure. That's kind of tautological. Let me explain what it means. Okay. What this means is that so it says that if E is an E, then F plus or minus N times E is N times F plus or minus E. So i.e. The plus or minus 1 action is equivariant, or the map is equivariant. Let's say the maps are plus or minus 1 equivariant. Okay. Okay, so the next thing we want to define is we'll define the category of Torsors. Okay, so now I'm going to define the Torsors. So, definition. So we define the category. So I'm going to write it like this. We take these Torsors modulo this action. So this is going to be the divide on time, or sorry, the additive action. So where by the following, the objects of this category are going to be polymorphisms of bijections from set T to FL viewed as an FL torsor. So we're always going to view this part as an FL torsor. So that's more relevant in the morphism. And the polymorphisms, the polymorphisms are orbits. So that describes what the objects are. The polymorphism is an FL divided on times. So this is a orbit of a single bijection F from T to FL. So i.e. This guy here is equal to FL divided on times. So these are just affine linear maps composed with F, okay? And then the morphisms, so a morphism from F to G are given by alpha from, oh, now we're not using, did I use T or E? I used T. So TF to TG, so I'm going to use this notation. So this is the underlying set of E and G, such that F is equal to G composed with alpha. Okay, and then so the composition, so now we just check the composition. So this is a category, we have to check the thing. This is similar to the these groups modulo plus or minus 1. Okay, so that's what the composition is, and so again the notation. If E is an E, then, oh, sorry, I already did this. So we simply denote an FL torsor modulo this group action. So this is this plus or minus this dihedral action by simply F this thing or T if we have this thing. Is such an object. Okay, so now I want to talk about some subgroups. Okay, so let's do another definition. So let this guy here, T, be an FL torsor up to the dihedral action. Okay, and so we're going to define a subgroup out plus of T. And so this is the same thing as you know, if I were going to do it with the F. But this is going to be defined to be equal to the set of alpha from T to T. So these are bijections of sets. Such that, okay, so this guy here, I need to fix some notation. And then we'll take FT. Okay, so we're going to take this orbit of a particular fixed FT. Okay, and then for this particular FT, so we're making a choice here, there exists a lambda in FL such that for all E in E, FT composed with alpha of E is going to be Ft of E plus lambda of alpha. Okay, so let's note that this depends on a choice. Okay, and I want to show that it's independent of the choice. So we want to show, let's show that out plus t is independent of the representative ft. Okay, so let's prove this. So how do we get another representative? So to all the other representatives are just orbits of this guy here. Okay, so in particular, let gamma from FL to FL be defined by, so we're going to let it be in this group and we're going to suppose that it has the following structure. So we're going to write mu sub gamma of z plus lambda sub gamma, mu sub gamma here. This is in plus or minus 1. The lambda gamma here. This is in FL. Okay, and now what we're going to do is we're going to look at how we're going to apply this definition here to our transformed guy. Okay, and then we're going to check that the transformation is still linear given that it was for ft. So we take gamma composed with ft and composed with alpha. Okay, so this is our new representative here. We compose it with alpha, and then we plug in E. Okay, so this guy here is going to be gamma applied to ft composed with alpha of E. And we know how this transformed. So this was equal to ft of E plus lambda of alpha. Okay, and that was from the definition before. And so now we look at how this is defined. So this is star. Okay, I'm going to go to the next page. Oh, 1 second. Okay. Okay, so I'm going to go to the next page. So star is now equal to mu gamma ft of E plus lambda of alpha plus lambda of gamma. Okay, and so now this thing here is really, so there's a couple things to observe. Okay, first of all, this guy here, this is mu gamma ft of E plus lambda of gamma plus mu gamma of lambda of alpha. Okay, so we have this dude here. This is really gamma composed with ft. So this is our new guy, E plus mu gamma of lambda alpha. And so this is still, okay, so this is still a translation. Okay, in which this implies that this group here is independent of representative of this polymorphism. Okay? T. Okay, so All right, that's nice. So maybe we could still worry that we could have two representatives and perhaps that alpha collapses them into a single representative. So that's something that we could worry about. So let's check if there's multiplicity, and to do this we need some notation. Okay, and this is how we'll do it. We'll define, so we'll take gamma composed with ft, so we pick our fixed representative, and then we'll compose it with alpha. And then this will be defined to be equal to gamma of alpha composed with ft, right? So this action here will induce an action on the set of polymorphisms, okay? So in particular, alpha maps this guy here to this guy here. And we can figure out what mu of gamma of alpha is and what lambda of gamma of alpha is. So this was just mu gamma, and this was mu gamma lambda alpha plus lambda gamma. So we can check that the action is well defined. So now let's check that everything's okay. So we check that this action doesn't collapse the polymorphism. So gamma, so if we have two morphisms here, and we suppose that they're equal, okay, then this tells us that we'll have well, let's just write down what these two things are. So mu gamma of alpha, this is equal to mu gamma from what we saw before, gamma 1. And then we saw lambda gamma 1 of alpha. This is equal to mu gamma 1, lambda of alpha plus lambda of gamma 2, or gamma 1. And then we do the same thing over here. Gamma 2 of alpha, this is mu gamma 2, lambda of alpha plus lambda of gamma 2. And then mu of gamma 2 of alpha is equal to mu of gamma 2. Okay, and so if these guys are equal, then we're going to have these two be equal and these two be equal. Okay, so if they're equal, so we're supposing this, then mu gamma 1 has to be equal to mu gamma of 2. Okay, and that's coming from this first set of equations here and here. Okay, and then from the second set of equations, we get that that mu gamma 1 lambda of alpha plus lambda gamma 1, and then we have mu, well, it's the same thing. We had mu gamma 2 before, but this becomes mu gamma 1 of lambda of alpha plus lambda of gamma 2. Okay, and then these get canceled here, and so this implies that lambda of gamma 1 is equal to lambda of gamma 2, so which tells us that gamma 1 is really gamma of 2. Okay, so they're exactly the same. So the action of translation of polymorphisms is well defined. So let's say the action of a polymorphism, yeah, it's a set, is well defined. Okay, so that makes sense. Now I'm going to make one more definition, then we're going to return to this in a moment. So let's make a definition. So this guy here, so we're going to take T, this torsor, so this is just going to be defined to be equal to the alphas, which are bijections. Okay, and again, this is going to depend on a representative, but we show that it's well defined. Ft composed with alpha is equal to gamma of alpha composed with ft, where gamma of alpha is in FL divided on times. Okay, so so checking that this is well defined. So checking is similar to this out plus. Okay, so in particular, we have this kind of inclusion of out plus inside this dude here. Okay, so that's all I want to say about that. Okay, and so now I want to go back to a little bit more about the structure of this guy here. So okay, so let's let T be an FL torsor modulo this dihedral action. Okay. We can see that this guy, so the obvious fact, I guess you should never say obvious, but if you have an additive group of automorphisms, it's an abelian group. Okay? What is not so obvious is that, so less obvious, less obvious is the fact that that T, this guy here, can be given a, let's say, FL group modulo plus minus 1 structure. Okay, so this is a less obvious fact. So, all right, and this is going to depend on representatives again. So, the idea is, okay. So let's talk about the construction. So pick any representative. Let's say ft of ft. Okay, then define this guy here. Okay, so now I'm gonna take this torsor and I'm gonna make this guy here, and it's gonna be defined to be equal to plus or minus 1 times the map alpha goes to lambda of alpha, where ft composed with alpha is equal to, let's say on some e, is equal to ft of e plus lambda of alpha. Okay, so this kind of uses all the things that we talked about. So we saw that this group here was defined to be the dudes that translated by a single guy with some representative. It turns out that this doesn't matter. The representative doesn't matter. Okay, and so what I'm going to do is I need to construct. Okay, to remember to construct a group up to plus or minus 1, I need to give. What I need to do is I need to give a map here, this polymorphism from here to FL. And so we kind of have G and maybe minus G. Okay? For some G. And my claim is that this G, right, this is our G. This works. Okay? And so alpha is in here, right? And it maps to, well, it'll map to two things, right? A plus copy and a minus copy, but it'll map to lambda of alpha. Okay, and this lambda of alpha is well defined up to plus or minus 1. Okay, so that actually can be seen from our previous computation, but to do this, let's pick another representative and show that it's well defined. So to do this, to see that this makes sense, this polymorphism is well defined. So pick another representative. Gamma composed with Ft. Okay, so where gamma is now in Fl, this dihedral group of order 2L. Okay, then we just compute. So gamma composed with Ft, composed with alpha of E. Okay, so this is, again, I'm just going to do the exact same computation I did before. So mu gamma this guy plus, and okay, and we see that mu gamma lambda alpha, this guy is in lambda of alpha, negative lambda alpha. Okay, and hence the map is well defined. So this implies well defined. So this thing's well defined. All right, so that's all I have for you in this video. I want to use this for constructing the Hodge theater. So that's what this was all about again. Thanks for watching.